हेलो हेलो। हाँ सर जी। हेलो। हाँ सर जी बोल रहे हैं कि क्या करिए ना कि सेटिंग में जाके थोड़ा सा चेंज कर लीजिए ना, ये लोग पार्टिसिपेंट को ऐड करने के लिए ले लीजिए, क्योंकि मेरा फोन हैंग कर रहा है, वो सेट ही नहीं हो रहा है सेटिंग। ठीक है ना सर?
होस्ट में ना फर्स्ट।
मैं आपको होस्ट बना रहा हूँ।
Hello, audible?
Audible, sir.
Okay. We have discussed the transformer here. So ideal transformer, as we discussed, what is the zero leakage flux? Okay. So how to minimize the leakage flux? That flux produced by primary and secondary, if it is confined within the core, then there is no leakage flux. There was one question they asked how to minimize the leakage flux. What is the leakage magnetic?
दे दे हमें.
So by two methods, overlinked and multi-stepped core we are using, so that we reduce the air gap and leakage flux is reduced. Now winding is also no resistance. Infinite permeability core. Yeah, this is another how to reduce the core leakage flux. If your core material is of high permeability, then maximum flux is passed through this. Correct, no? So this reluctance of core is zero. Negligible current means required to stabilize the magnetic flux. Magnetizing current means I mean. And core loss. Core is loss free, so there is no magnetic loss, no copper loss. Now this we have already discussed how this is the ideal transformer. You know, the ideal transformer, when it connected to supply, it take only magnetizing current. So this is here magnetizing current. Okay. IM means we are denoted with I mu. Okay. That produce the flux. So this ideal transformer only draw the magnetizing current, no loss component also at no load. P1, V2, I1, I2, IM, E1, E2. Okay. Got it? V2 is the terminal voltage, V1 is supply voltage. I mu. Actually, IM, in our derivation, we denoted with I mu. Okay. That is magnetizing current, passive component of no load current. Okay. Now suppose if we have as I told, practical transformer at no load. Practical transformer at no load, then there is a complete magnetizing branch. It has a resistance and reactance in parallel. Then I node with a angle phi node. Correct, no? Then two component of this I node. Okay. Now, my dear, this is the exact vector diagram. Here we assume, see, no voltage drop in the windings, means impedance we neglect. Then if we connect the load on secondary, as referred to primary side, see this primary current I0 plus I2 dash. Correct? Okay. If no voltage drop in winding means equal number of here, because E1 equals to E2, it means equal number of turns. If we make a like E1 is greater than E2, then E1 is big, large phasor. Okay. here we same number of turns, that's why this E1 equals to E2 also. Okay, so as you know, first we draw the I naught. Okay. Here this diagram. It is. So this I naught has a two component, correct? One is here, another is here, this side. Okay, this and this, correct? This and this. Okay, dear. So this is I mu or Im, that is magnetizing component. That is I naught sine phi naught, magnetizing current. This is loss component, I naught cos phi naught, correct? Okay, because this is the phi naught angle power factor here. Cos phi naught is the no load power factor, no load power factor. Then because if maybe this here it considers same number of turns. If primary is HT, means large number of turns, then this is E1. Okay, not this. Then E2 is also in same phase. This is E2. And E2 equals to V2 because drop is neglected. No voltage drop. No voltage drop in primary and secondary. It means that is equals to, this is equals to E1. V1 equals to E1 and V2 equals to V2. E2 equals to V2. Okay. Then now if load on secondary, here it is a lagging power factor, then your current I2 is lag. As referred to primary side, it is I2 dash equals to KI2. Okay. Now you know this two current vector sum of this I2 dash and I2. Okay. This I1 equals to I0 plus I2 dash. Their vector sum. Okay. Then how we calculate the vector sum? Actually, we can easily calculate I1 if we know the angle between this angle. Okay, but this angle is not mentioned here. This angle is not available. Okay, between these two vectors. Otherwise, this I1 we can calculate equals to I2 dash square plus I naught square plus twice I, like you know, R square equals to P square plus Q square plus twice PQ cos theta. PQ cos theta. Or if this is required, okay, but here this angle is not there. Then similar to the, as we resolve I naught, we resolve the I2 dash also. See, like we take here this and this. Two component of I2 dash. It become I2 dash sine phi 2. Because this angle is also phi 2. Okay. This phi 2. This is also phi 2. Okay. and this is I2 dash cos phi 2. Okay, now there is a total component. If they add now is, hello, if you do the sum of these two vectors, we remove this. Okay, so if we add this plus this, okay, vector sum of this, we gave a total vertical. Here we get a this plus this, we get a total along x-axis, along y, this is y. Okay, then we can easily calculate this I1. Okay, because we know this IY, IX. Okay, this is your this will now give you now this is the phi 1 angle. Now you along this axis, you know there is a V1 also, and this V1. Now this is your primary power factor angle. So we can calculate cos phi 1 and I1. That will give you primary power factor and primary current. Okay, this is the we do as a revision. Correct? Got it?
Yes, sir.
Yes. Yeah, great. Now come to continue. Now, if we go for a further, your practical transformer with voltage drop also, we consider the impedances also, primary, secondary. Then lagging unity, leading power factor, lagging power factor. Okay. So as I told ना, please you draw this diagram. अभी देखो आप लोग ना क्या करते हैं, जैसे क्वेश्चन आता है व्हाट वी राइट, यू आर नॉट सर्चिंग एक्चुअली, यू डू सम रिसर्च वर्क. ओके, व्हाट इज द लीकेज फ्लक्स, परेशान है व्हाट इज द लीकेज फ्लक्स. so see, this is the diagram, it represent, okay, it represents, see, the flux, maximum flux produced by primary, it is confined within the, see, here is a 3 flux na, due to first is due to at no load, this one, when load, due to secondary current, there is another flux. इस डायग्राम को हम कॉपी कर लेते हैं ना, and I put in group also. Here you can compare the leakage flux, and then due to leakage flux there is a leakage reactance. So here, suppose this load is not there, then this current is 0. Only transformer draw here, no load current. Okay. Due to this no load current, there is a, this is the flux. This will give you flux, phi naught. Okay. But when we put the load on secondary, we connect the load. Now there is a I2 current, load current. Due to this load current, there is a, because this current is flow, like here, so there is another flux will come here, phi 2, due to this. So initially the flux due to primary current, then due to load, secondary load current. Okay. Now this flux is reduced because this is in opposite to this. So now your transformer draw the more current from primary. So it is not now I naught, it is I1. Okay, and this become I naught plus I2 days. Okay, this as refer to secondary primary side, this I2 days. Okay, I2 days equals to KI2, that is primary side. Okay, now means if there is more current from primary side, then another this flux is come phi2 days. Now due to this I2 days current, there is another flux is come in this line, that is phi2 days. Okay, so actually these two flux are opposite. Then net flux is, in net flux in your core is phi naught plus phi2 minus phi, again this is in opposite, no? Phi2, phi2 dash minus phi2. They have cancelled each other, then net flux is always maintained in the core is phi naught. Okay, correct. Now my dear, come to the leakage. See, maximum flux produced by primary and secondary winding, they are within the core only, this core. Okay, but due to this sinking effect, some flux here like this. Okay, this is called primary leakage, secondary leakage flux. Due to this primary leakage flux, there is an inductance. You know what is the inductance? Leakage, total leakage flux. It is leakage divided by per unit of current. That is called inductance. It is in Henry. Means leakage flux of primary divided by your current of primary. It will give you L1, L2. Okay. There is a L1, L2 is leakage inductance due to leakage flux. Then XL equals to omega L. So for primary, the inductance is omega L1. Then due to leakage inductance or leakage flux in secondary, there is a secondary leakage reactance. So this is your leakage reactance of primary and secondary. Okay. Now, if we minimize the leakage flux, this this inductance are reduced, L1, L2. This L1, L2, this phi1 leakage flux is secondary leakage flux. So this is reduced. If they reduce, their low value, if leakage flux is low. Okay, if these are low, means your inductance is low. If inductance low, means their reactance is low. If reactance is low, then total equivalent reactance of transformer is low. Then good value of regulation, means your voltage drop, internal voltage drop is less. Okay, dear. So this is the main flux and your leakage flux. Okay, leakage magnetic flux. If you draw this diagram and you show leakage flux, then leakage reactance, you correlate, you get a marks, good marks. Now due to leakage resistance and leakage reactance, there is a drop in winding. Okay, so this is your at unity power factor, but at lagging power factor, this is the diagram, vector diagram. Okay, these are not asked. Okay, but you now see here, I will explain this also. Phasor diagram of transformer at lagging power factor. Huh? Actually, when there is no drop, na, means this V2 equals to, here it shows the secondary is a high HV side, okay. So see, now this is your secondary voltage, V2, this. Then this is your resistance drop, 2 to R2, drop in resistance, which is in phase with current. This is your load current. Now it is lag, means this I2 is lag. Current I2 is lag this voltage V2. This is your V2, this is I2. Then now, as I told, the drop in resistance in secondary, this is, parallel to current. That's why we make a parallel to current. Then drop in reactance X2, this is this. Now, this is the total drop in impedance due to secondary impedance Z2. But it does not show this. Now total voltage is, this is your E2. Okay, so this diagram we make. This is the we make when we calculate the voltage regulation. Now not only it is here it show only the secondary side. Like this is your V2. Then your current is lag. This is your V2. Sorry. This is your V2, then current is lag here. This is your I2, okay? It lag with phi2. Now drop in resistance in parallel with current, so it is like this. This is your current drop in resistance. Due to secondary resistance only. Here we not consider the total resistance. Here only the secondary side. Then the drop in reactance, it is perpendicular to this. It is this. This is I2 X2. Now this plus this plus this all three will give you this. This is your E2. Because in induced voltage in secondary, then there is a resistance of secondary reactance, and this is your load. This is your secondary circuit. Here it is a V2, this is X2, this is R2, and here is a current I2, load current. Okay, this power factor is cos phi2, lagging, and here it is your E2, no load voltage. Okay, so this is the diagram. Here it is show V2, then this I2, these are the drop, then this is E2. Okay, got it? But this will not ask. Just you remember the yesterday's the voltage regulation with respect to primary and secondary. Okay, that is very important because numerical is asked on that. Now come to maybe this there is a load on transformer. It may be unity. Then see secondary voltage and current in same page, unity power factor. But at lagging power factor, the current is lag. In leading power factor, see V2 is here, I2 is lead the voltage. Okay. Okay. Now you come to the at no load. No load. When transformer at no load, only the magnetizing branch is there. So you take a I naught only. Then power, I naught has a two component, okay, active and passive. We represent with I mu and I omega, okay. So by no load, we calculate magnetizing branch parameter R naught, X naught, I naught, two component of I naught, and core losses. Is power input to at no load equals to core loss. So this is the open circuit. This equivalent circuit we already explained. Okay. Now you come to how we transfer the parameter from like as referred to primary side, as referred to secondary side. It is very important. So today I will this. For this only we connect so that we in evening we can solve the numerical based on this. You come to here again. Yes. When we transfer from this secondary to primary side or primary to secondary side, we continue extend this. Okay, dear. So see, no. How to, actually when we transfer the parameter, your performance should not change. Performance means losses or like voltage drop in reactance and resistance. As referred to primary side, your total equivalent resistance is R01. See, if we calculate total copper losses, please remember, if total resistance is R01 as referred to primary side, then we take a primary current. So this will give you total loss, total copper loss as referred to primary. Or either you individually add primary current, primary resistance plus secondary current, secondary. Correct? Okay. This is your total copper loss. Now if we calculate R01, my dear, what is the value? See, I1 by I1, then it is I1 square by I1 square, it is cancelled, so it is give R1 plus, if this is divided, that it is I2 by I1 whole square, R2. Now you know K equals to turn ratio. If we take V2 by V1 equals to I1 by I2. If it is I2 by I1, then it is 1 by K. So we can write now R2 plus 1 by K square R2, or R01 equals to R1 plus R2 by K square. Sorry, K square. It means that is known as a days. So what is the value of R2 days as referred to primary side? Hello? It is C. It is divided by K square, turn ratio, R2 by K square. Then similarly reactance, I2 days, it is also R2 by K square. Now this is the resistance. Now if current already we calculated, I2 dash equals to KI2. Current is multiple and voltage is V2 dash equals to V2 by K. Voltage are divided. Please remember. Okay. Okay. Hello. Current is multiple, voltage is divided. Like we write E2 dash. E2 dash equals to, it is E1. E2 dash equals to E1 means it is E2 by K. Let us here, because turn ratio of transformer. Hello. K equals to E2 by E1. Sorry. E1 V2 by V1 N2 by N1. This is the turn number. Actually, K is going there, of course. My dear, if we calculate E2, E1, this E1 equals to, from this equation, E1 equals to E2 by K. E2 by K is what? It is E2 days. It means E1 equals to E2 days. Okay? Yes. So this is your E2 by K means E2 days. Okay? So please remember, when we transfer the parameter from secondary to primary, then resistance are divided by K square. Resistance, reactance, impedance also, like Z2 dash equals to Z2 by K square. Okay. Current is multiple, voltage is divided. Okay. But when we transfer from secondary side, so just reverse. Like here you can apply the total copper loss as referred to secondary side. Then if we take a secondary current, total resistance. So it is I1 square R1 plus I2 square R2. Okay. Then R02 equals to, now it become I1 by I2 whole square R1 plus this is R2 only. R02 is the total resistance, equivalent resistance as referred to secondary side. That is R2 plus R1 days. R1 days means R1 days equals, R1 days means I1 by I2. It is K, means K square R1. Okay. So in this case now, when we transfer the primary side parameter to secondary side, from primary to secondary, then I1 dash, X1 dash, and other is also, so they have K square R1, K square X1. Okay. So this is the parameter. Impedance will be also impedance, resistance, reactance, impedance. They have multiple by K square. Even we transfer the magnetizing branch parameter. They also multiple with K square. Okay, please. Okay, dear. Now, but current here, when we calculate I2 day, I1 day equals to, it is now divide I1 by K. Please remember I1 by K. Why? Current is divided. Now voltage are multiple. I1 day equals to K V1. Okay, got it? E1 days also, KE1. Okay, it is just opposite of this. So from one side you remember, other side is mirror image, opposite you do. Okay, now we can calculate now. Okay, आप इसको रेफर कर सकते हैं. We have put in group. Okay. This is the important part of transformer. Okay, dear, how to transfer the parameter? K is the turn ratio. Then this is the secondary side parameters. Resistance, reactance, impedance are divided by K square. Voltage is divided by K. Current is multiplied by K. But when we do transfer the primary to secondary side, then resistance, reactance, impedance are multiple by K square. Voltage is multiple, current is divided now. I note also. X0 also. Similarly, we can transfer the R0 X0 also. They are multiple with K square also. Okay, this. Now total equivalent resistance impedance as referred to primary side. Now we do the testing, because from open circuit, short circuit test we calculate this circuit parameter, equivalent circuit parameter and copper loss and iron loss. Then we can calculate by testing, we perform certain tests on transformer like measurement of resistance, winding resistance, then measurement of iron loss, full load copper loss, then equivalent parameters. Then we can calculate the performance. Performance means efficiency and voltage regulation. So by no load test, we calculate the no load current, then two component of no load current, then equivalent magnetizing branch component R0 X0, and no load losses, that is core loss. Okay, Then in short circuit, we do the LV side short, we apply the reduced voltage. Okay, then we calculate, either Z0, X0, R0, either primary side or secondary side. We can to predict this parameter required to determine the voltage regulation. Then we calculate the copper loss also, that is required to calculate the efficiency. So your one numerical is based on this. They give the open circuit, short circuit parameter. We calculate this parameters and losses. Then we calculate the efficiency. Okay. See here, this is your during short circuit test. The short circuit power input is this. Then we calculate R01, then Z01, then X01. This is very important, my dear. Okay. From short circuit test data. This is used in your numerical. Okay. Excellently. Now regulation. Okay. So this is the formula: no load secondary voltage minus full load divided by sometimes no load, actually with respect to no load. Sometimes it is with respect to full load also. Okay. इसको actually no load के with respect में रखते हैं हम. Okay. We calculate with no load, then voltage drop. Okay. This is your voltage regulation formula. Yes, here we calculate this voltage regulation. No load terminal voltage, either on primary side or secondary side with respect to. Okay, so as referred to, if we write as refer to secondary side, means we transfer the all parameter with respect to secondary side. Then percentage voltage regulation equals to this no load secondary terminal voltage minus full load secondary terminal voltage divided with respect to no load. Then this, so it will give into 100. By this you can get a percentage voltage difference. Now E2 by V2 from this phasor diagram, we calculate as referred to secondary side. I2 R02 cos phi 2 plus I2 X02 sin phi 2. This difference E2 minus V2 divided by E2. Okay. So it will give the percentage, maybe like it is 5% or 8%, whatever it is. Correct? This value suppose. Now they asking terminal. When we calculate a voltage regulation, then here in first part they ask voltage regulation. In second part they ask terminal voltage. So because percentage drop, it means there is a 5%. So E2 is given. E2 is your 415 volt. Suppose it is given. Okay. Then V2 is the terminal voltage. Okay. No. Then we can calculate E2. In E2, how much percentage drop? 5%. We calculate 5% of E2. Then it is E2 means 415 minus 5% means 0.05 into 415. Sorry, 415. then this will give you terminal voltage. Okay, this is in your numerical. This ask they give the power factor. They give cos phi 2 like 0.7 lagging or leading. Lagging. This is for lagging. For leading, it is minus. Okay, then sin phi 2 you calculate. Like if it is 0.8, then it is 0.6. Okay. Now R2 days we calculate from copper loss, no? And R2 we calculate total equivalent. Then Z02 it is no, this is not secondary side, no, primary side. This is second. Now either if you calculate na, see first we calculate R02, that is where short circuit loss divided by actually I1, because primary side we give na. Okay, I1, this will be your ISC squared. Then we calculate Z01 also, that is voltage applied by current V by I is the Z. Then you calculate X01 from Z01 square minus R01 square root. Now this parameter are on primary side. You can calculate on secondary side. Either you change this formula, or either you determine this parameter as referred to secondary side. As referred to secondary side, you have to calculate R02, X02 and Z02. Actually Z02 we required R02, X02. Okay, so this is, when we transfer this, you use the K square, but individual we don't know na R1, R2. That's why. Okay, if primary side parameter are given, then what you do? We change we use the primary side voltage regulation formula. See, as referred to primary side, as referred now, if you primary side, voltage regulation, it is, we take a I1, then R01 cos phi 1. Okay, now at lagging power it is plus I1 X01 cos phi, sin phi. This is your drop divided by. Now here we write V1. V1 is I. Okay. As a percentage, you multiply by 100. Okay, dear. As referred to primary side. As referred to secondary side, this. As referred to primary side, this. Now at leading power factor, it is come minus. At unity power factor, please you use this. Or as referred to primary side. As referred to primary side. This is secondary side. Primary side, this is your V1 voltage. Now at unity power factor your current is in same phase. This is I1 at unity power, because phi is 0 degree. Phi 1 is 0 degree. Now drop in resistance, total drop, that is I1 R01. This is drop in reactance I1X01. This is your this will give you this will give you E1 will give you V2 dash. Here it is not E1. This is actually here it is V2 dash. V2 dash. Okay. And एक मिनट Okay. Hello. So we use this. Okay, dear. So today evening we solve the numericals on losses, efficiency, and this. Okay. I think now you clear everything, because definitely the question is asked in transformer. Okay. So today evening we complete this transformer. Okay. Then we start alternator. Okay. Synchronous machine. Hello.
Yes.